recent World's Strongest Man competition, Brian Shaw pulled a bus with a mass of 6,400 kilograms. The average coefficient of kinetic friction between the bus and the other parts is estimated as 0.25. If Brian pulls with a force of 24,500 newtons at an angle of 15 degrees above the horizontal, what is the acceleration of the bus? Now we're asked to find the acceleration of the bus, which means that it is not in equilibrium. We start the same way no matter what. We have a free body diagram. So there's a dot representing the bus. We always have the gravitational force, which is straight down. And then there is a surface. The bus is being pulled on a road, and so there is a surface. That means that there's a normal force. Normal force is going to be upward. There's also a frictional force because it talks about the coefficient of kinetic friction. The bus is moving, so it's kinetic friction. I'm going to have my thought is that the bus is going to be moving to the right, and so therefore the friction is going to be to the left. It is parallel to the road as well. And once again, it is kinetic friction since the bus is moving. The next thing here is that there is a force applied by Brian Shaw. He applies a force of 24,500 newtons. Usually this is through a string rope or cable of some sort that is attached to Brian. You could really label it either way, as an applied force or a tension force. An applied because it's applied by a person, or a tension because it's through a rope. I'm going to label mine as an applied force, and it's at an angle of 15 degrees above the horizontal. We want to figure out the acceleration of the bus based on all of this. We're going to start by writing down our givens. We are given the mass of the bus is 6,400 kilograms. We are also given that the coefficient of kinetic friction between all the moving parts is 0.25. We are given that the applied force is 24,500 newtons. And as always, we know that the gravitational field constant is 9.81 newtons for every kilogram. We're going to figure out what is the acceleration of the bus. Now what we're going to do is we're going to take this applied force, just as we've done before, and we are going to break it into its x and y components. Since we're given the mass, we are also going to solve for the gravitational force. Let's do that first. So whenever you're given the mass, solve for the gravitational force, m times g. Mass is 6,400. G is 9.81. And we get that the gravitational force is 62,784. As always, forces are in newtons. Now, just like I did before in equilibrium, I'm going to take this applied force and break it into its x and y components. I'll redraw this triangle. We are given that the applied force is 24,500 newtons. We're given that the angle is 15 degrees. And we are going to solve for the x and the y component. We'll start by labeling our sides of our triangle. We are given that this longest side is the hypotenuse. The angle is on the left. The opposite of left is right. So our y component is the opposite side. And the one left over, fx, is the adjacent side. We're going to use our SOHCAHTOA to solve for those two components. Let's solve for fx first. That is the adjacent side, and we know the hypotenuse side. So we're going to use the cosine. We have that the cosine of 15 degrees is the adjacent, which is fx, divided by the hypotenuse, which is 24,500. Now remember that this cosine of 15 simply represents a number, and in this case, you either look it up on your trig table or type it in your calculator. It is cosine of 15, which is 0.966. And that is equal to f sub x over 24,500. We multiply each side by 24,500, and we get that the x component is 23,665. All sides are newtons, since the hypotenuse is also in newtons. Next, let's get the y component, that is the opposite side. Again, we know the hypotenuse side, so we're going to use sine. Remember that this sine of 15 degrees simply represents a number. You can either look this up on your trig table or type it in your calculator. Sine of 15 is 0.259. Multiply each side by 24,500, and we get that the y component comes out to be 6,341. Okay, so now what we're going to do is, again, we're going to replace this one component, or this hypotenuse, I should say, with its two parts, with its two components. So I'm going to redraw this triangle, but without the applied force. Instead, I'm going to have its two components drawn. We have our gravitational force down. We have our kinetic friction to the left. We have our normal force, which is up. And then we have our two components that we just solved for. We have the x component to the right, and we have the y component, which is up. Now, because we are not in equilibrium, it says that it accelerates. One of the directions will not cancel out, but one of the directions still cancels out. Again, this is what's going on here is we have this bus being pulled by Brian Shaw. As such, the bus is not moving up and down at all. So the up and down components still cancel each other out. It is the left and right components, or the left and right forces, that don't cancel out. But the up and down still cancel out because the bus is not moving off the road. And so therefore we have the normal force and the gravitational force. Those used to always be the same as each other. But now we have this y component. It belongs on one of the two sides. The y component is also up and down. So does it belong on the side of the normal force? Or does it belong on the side of the gravitational force? Well, it is on the same side of the dot as the normal. Both the normal and the y components are up. So they belong on the same side together. It is the y component plus the normal which balances out the gravitational. And so what we get here is we just solve for the y component. The y component we said was 6,341. We don't know the normal force. We did solve for the gravitational force. We said it was 62,784. Now we solve for the normal force by subtracting the 6,341 to the other side. And we get that the normal force is 56,443 newtons. Now the next step that we have to do is we're actually going to solve for the kinetic friction. We're going to do so by using this formula. The kinetic friction is the coefficient times the normal force. We were given that the coefficient of kinetic friction was 0.25. And the normal force we just solved for as 56,443. When we multiply, we get that the friction is 14,111 newtons. Now remember, our main objective here is to solve for the acceleration. So now what we're going to do is we're going to say that the total force, now this is only in the horizontal direction, the x direction, is equal to the mass times the acceleration. Now the forces in the x direction, we have Fx and Fk. Fx is to the right, so it is positive, and Fk is to the left, so it is negative. We solve for Fx. Remember back here, Fx is 23,665. We just solved for Fk. Fk is 14,111. We know the mass. The mass was 6,400 kilograms. And then we're going to solve for A. So first step here, we're going to subtract the 23,665 minus the 14,111. And we get 9,554 is equal to 6,400 times A. And then finally, we divide each side, since it's connected to the A through multiplication. We divide by 6,400. And we get the acceleration to be 1.49. Acceleration as units of meters per second squared. So as before, what we did was we took our free body diagram, broke it into its x and y components, but in this situation here, although the up and down still balance out, the left and right did not balance out this time. Instead, the left and right added up to equal mass times acceleration. That's the difference between this type of problem and the old equilibrium problem.